All right, let's play with rules of inference. So let's pick out a homework problem. Let's take a look at question 4, part A. So this is a proof question, but it's written in that horizontal format. So I'm going to copy down what this says verbatim, and then we'll change it around. So P implies Q, not R implies not Q, not R. All of that leads to not P. So I could write this as follows. Statement 1, P implies Q. That's given. That's a premise. Statement 2, if not R, then not Q. That's a premise. Statement 3 is not R. That's a premise. And check in every now and then. Make sure that the things you're writing down are propositions. Right? We know that an if-then is a proposition, but not R is actually a proposition. It says the negation of R is a true statement. Or equivalently, it says R is a false statement. That's a proposition. All right, and what we want to conclude is not P. I'm not going to write that down yet because I haven't proven it. I'm given these three things, and I want to get to not P. And usually I look in my things that I'm given and I will see, is there a not P somewhere? And if there is, maybe I can somehow conclude that. I don't see any not P's. I'm going to have to do some kind of negation somewhere. So what's something we might do here? Good old contrapositive, right? Applied to this first thing will tell us not Q implies not P. That's a contrapositive of 1. What next? And there's multiple ways we can do this. There's more than one correct path. Chain rule on 2 and 4? Not R implies not Q implies not P. Why not? Chain rule 2 and 4. Other ideas? And our goal is to try to put things together or simplify things or change things around in a way that lets us put things together or simplify things. Ultimately, we want to get to something really simple, which is just not P. So at home, right, you would stare at the list of implications from the book, and you'd think about each one, and can I apply this here? Yeah?
Then we have direct reasoning.
Okay, which rules?
For 5 and 3.
5 and 3, perfect. So if we put 3 and 5 together with direct reasoning, not R implies not P, and we're told not R, we can conclude not P. That's direct reasoning or detachment. 5 and 3. And what do we say at this point?
QED.
QED, which is Latin for thumbs up. Right, that's what we were asked to demonstrate. So there's a completely valid proof that not P follows from those first 3 statements.
So an invalid proof would be one in which somewhere along the line you used some justification that was not actually one of our rules.
Right. So if we did something like a fallacy, for example, that will invalidate your proof. Or if you write something down like not P before you've actually shown it, right, that invalidates your proof. Okay, so this is called a direct proof. A direct proof, you start with things which you are taking to be true, and then you apply rules of inference so that everything that you conclude is subsequently true, and ultimately you conclude the thing that you're trying to show, which now you know that is true. That's your direct proof. It's working very directly from what's been given to you to what it is you're trying to show. And direct proofs are sort of the first thing that occur to us usually, but they're not always the easiest way to prove something. So there's a different thing we can do which is called an indirect proof. And let me see if I can motivate the idea of an indirect proof. We're given P, which might be, this thing is true and this thing is true and this thing is true. I wouldn't call it P because P means this thing. But I'm given some proposition that I'm taking as being true, and I want to conclude from that some other proposition Q is true. So I want to start with P and do some stuff and eventually conclude Q. That's the direct approach. There's a different way I can do this. Basically, we're trying to show that this is true. Well, this is logically equivalent to this, the contrapositive. So if I can start with assuming that the conclusion is false, and I can eventually show that my premise must be false, that's enough to say, hey, I've proven if P is true, then Q is true. So basically a direct proof of the contrapositive is as good as a direct proof of the original statement. So let's use an example of this same question. We're given those three things on the left and we want to prove the thing on the right. So an indirect proof, I'm going to assume the negation of the thing I'm trying to show. And I'm going to say that's an assumption. And I'm going to prove that this and this and this logically is false. And then I'm going to conclude, well, since I know that the and of this and this and this, the conjunction of those must be true, then this must have been a bad assumption, because assuming this leads me to something which should be true being false. So basically I'm going to start by negating the thing I'm trying to show, and I'm going to argue till I get to a contradiction. Something that contradicts what I was originally given, or some rule of logic. If I can show that false equals true by assuming this, then I'll have to conclude not P must be true. So I'm going to do not P is my assumption, which means I can just assume P, that's double negation. And I'm going to assume my same premises. If P, then Q. If not R, then not Q. And not R. And each of those is a premise. But now I got P in my arsenal of true statements. And so what can I do with this to write another statement that follows from all of these? My brain always goes to direct reasoning. It's like the first thing that jumps out at me. And I got a P and I got an if P then Q. I'm going to conclude Q. That's direct reasoning 2 and 3. Can I do any other direct reasoning? Four and 5. 5 says not R, 4 says not R implies not Q. I can put those together and conclude not Q. That's direct reasoning 5 and 4. The order of these doesn't matter. And an astute observer will say, hey, I've just proven Q and I've just proven not Q. Something's fishy there, right? I'm going to drive that point home. I'm going to say, well, this is a true statement and this is a true statement, and so the logical AND of true statements must also be true. All right, that's just conjunction. And then we've got some property somewhere that says P and not P is equivalent to false. That's the negation law. Well, here we've got Q and not Q. That's false. That's negation law. Well, what have we done? We've just proven that false is true. Because everything that we write down in our proof is true, and we just proved false is true. That's the classic contradiction. And so I'm going to draw this sideways number sign and say contradiction. And then I can say, therefore, this original assumption, assuming that this was negated was true, must be incorrect, and so the original not P must be true. And that's what we were asked to show. So there's the end of my proof. So proof by contradiction, you simply start with things that you want to show. Assume that something that you're trying to show is true is actually false, and argue to an absurdity. Once you reach that absurdity, the thing that you assumed must have been wrong. And sometimes direct proofs work best, sometimes indirect proofs work best. To some people somewhere, they seem exactly the same. Same people who think KVL and KCL are exactly the same. Right? They really are in some sense, but to most of us they feel very different.
Are there any proofs you can do with one but not the other?
I don't think so, but it really depends on your definitions. Because we could use this line of reasoning in a direct proof in some sense. But on that note, let me mention something to avoid. If you're asked to do an indirect proof of this statement, technically this is an indirect proof, but it's not really, right? So your first step would be to say, let's assume the negation of this, so we assume P. And then you do all of these steps, which is really a direct proof of not P. And then you say, I got not P, but I also got P. That's a contradiction, so P must have been true. Well, you really did a direct proof, right? You simply assume that this conclusion was false, and then you directly proved that conclusion was true and said that's a contradiction. That's not really an indirect proof, right? Indirect proof, you want to start by negating this, and then you want to come to some contradiction other than, contradicting the thing that you assume directly, because that's a direct proof. And you can do an indirect proof that's really a direct, and vice versa. But there are definitely problems where one is a whole lot easier and the other one's really hard to imagine. And we'll see some of those with number theory. So let's look at this question. So this is 3A. So A implies B, C implies B, D implies A or C, and D altogether implies B. So let me write these out. A implies B, C implies B, D implies A or C, D. And sometimes you might not write down your premise until you actually need it, but I like having them right here where I can see them, so I'm just putting them down in the top. Is it plausible that this is going to be a true statement, other than because we know it's true because we're asked to show it? Logically, if we know that D is true, then we know that either A or C is true. We got two cases. If A is true, this tells us B is true. And if instead C is true, this tells us that B is true. So in either of the two possible cases, we know B is going to be true. So we're definitely going to conclude B from these four statements. But we got to put it into a very formal proof, right, using these rules of inference. So let me show you a way to do this, and this is not an easy thing to prove directly, but it's going to turn out to be very easy indirectly. We know that D is true, we know that D implies A or C, so we can conclude A or C. That's direct reasoning. 4 and 3. And we know A implies B, which means B or not A. That's conditional equivalence of 1. And C implies B, so we know B or not C. That's conditional equivalence of 2. And since this is true and this is true, they're logical and their conjunction is also true. That's just conjunction of 6 and 7. And now we kind of do the opposite direction of distribution, and we say that this is equivalent to B ORed with not A and not C. And that's just distribution applied to H. So right, we can take B or this, and we can AND it with B or that. So we're pulling the B out from inside. And not A ANDed with not C is the same as not A or C. That's De Morgan's theorem applied to the right-hand side of 9. And we know that A or C is true, so this is B ORed with not true. And that's just substitution of statement 5. And not true is false. And that's just negation. I don't know, not true is false. And we can come up, I got enough space. And B ORed with F is just B. And that's, I don't know, some kind of simplification. Identity law. And that's what we were asked to show. So there's a simple 13-step proof. And it's pretty devoid of intuition, to me at least. Right? We're just grabbing these things and putting them in and hoping that something simplifies down eventually. Let's look at an indirect proof. So we're going to have not B, that's an assumption. And we know that C implies B, that's a premise. Well, if C implies B and B is false, what can we conclude about C? Right? Those two go together and they give us not C, that's the contrapositive. 1 and 2. We also know that A implies B, that's a premise. And since we have not B and A implies B, we can conclude not A. That's the contrapositive of 1 and 4. So not A and not C. That's just conjunction of 5 and 3. Which means not A or C, that's De Morgan's theorem. And we know that D implies A or C, that's a premise. And so contrapositive one more time tells us not D, but we also know D is a premise. So there's your contradiction, and therefore B, and that's what we were asked to show.
If you confuse me a little bit on the left-hand side, in steps 6 and 7, where in the book it says P arrow Q is equivalent to not P or Q, and you commuted those two.
I commuted them, yes. So
I didn't
flip them around, yeah.
think a little bit.
All right, good catch. So technically, those have to get flipped. And then they'll get flipped in here, and I think that'll just put the B's on the other side.
But it's the same thing. But
It's the same thing, yeah.
But I just had to think of it to make it conform.
Right, right. So yeah, so quizzes and tests, I'll let you do commutativity in your head. But when you're writing this out for homework questions, just to sort of nail it down precisely, it's fun to actually flip them around and list the commutative property. All right, so we got direct and indirect proofs. You got some homework questions to play around with those. Is this making some sense? We're going to be doing this for weeks, so we'll get lots of practice on it. So your quiz Wednesday, you got 5 questions. I'll give you 45 minutes for it. You might not need 45 minutes. I'll give you 45 minutes, and we won't do it in the beginning of class. We'll talk about homework questions first. And then when everybody's comfortable, we'll take 45 minutes for the quiz. So your questions will be the following. Question 1 will be dealing with sets and doing set operations. Okay, you've done this in a homework. Question 2 will be proving a set identity using membership tables. And I'm pretty sure you've done this in the homework, and I think we did this on the board. Question 3 will be working with the notion of a proposition and what is or is not a proposition. Question 4 will be taking a statement and breaking it down into simpler propositions and then dealing with things like the converse, the inverse, and the contrapositive. And then question 5 will be something like one of these questions where I ask you to do a direct or an indirect proof. And I'll actually give you a choice. You can decide whether to do direct or indirect. So whichever one you like. So there's your quiz. And there's a homework question, which is question 4 from that section we were just working on. So play around with those, ask questions, chat in Discord if you like, and bring questions on Wednesday, and we can talk about them beforehand, before the quiz. Does that make sense?
Do we get any notes?
Yeah, you can use 4 pages of notes.
Can we use our previous homework pages for notes?
You can use anything you want for notes, but I'd rather you don't bring in your whole notebook because you'll spend your time flipping through it. So condense it down or use your homework.
4 pages is about the whole notebook.
Double-sided,
Yeah.
with no specification how big the pages have to be. So you can you know.
You're not putting a lot of restrictions on it.
Yeah. So my goal with this and 224 and such is not to restrict how many notes you get. It's really to sort of compel people to try to concentrate their notes on the stuff that they actually need to refer to, and the stuff that is in your brain, right, is most of it.
Well, I took a class about a year ago, and the teacher allowed one 8x11 page of notes,
Yeah.
and I crammed a lot on that one page.
Yeah. Those are some good note sheets.
Really, really slow. Small with the sharpest pins I could.
Yeah. And this course and other courses, a pretty good strategy can be, as you're working through the course, as you're doing the homeworks, right? You come into class, you take notes, you listen, you got the video and so on, but you go home and you try to make some notes of the relevant things that were discussed, the things that stood out to you and so on. And then when you're working on the homeworks, you try to work from your note sheet as opposed to the text or you know, your whole notebook of things you've written down. And you sort of adjust your note sheet in doing so. And when you're done, you know, you've got a subset of your notes, and you do the next homework and you use that, and maybe now you totally know what a union and an intersection are, so you don't need that on your notes anymore. So when you get to the exam, hopefully it's you know, a small tweak on your existing set of notes for what you want to do for the midterm or the final or a quiz or things like that. And then when you're done, you've got, you know, your one page that like replaces the whole course, and you can like sell that online or something. So that's a strategy. We got 5 minutes. Let me talk about even and odd numbers. So we're always going to talk about integers for a while here. So I'll say an integer, but I may stop saying that after a while. So an integer n is even if n is a multiple of 2. So 2, 4, 6, 0, negative 10, 2016. These are all even numbers. An integer n is even if n is a multiple of 2. N is even if and only if there exists an integer k such that n equals 2 times k. If and only if there exists, we haven't talked about these yet, but this is just shorthand for the words there exists. So n is even if and only if there exists some integer k such that n is 2 times k. So why is 10 even? Because 5 is an integer such that 10 equals 5 times 2. Why is 19 not even? Because there's no integer such that 19 equals 2 times that integer. In fact, 19 is 2 times 9.5, and that's just not an integer. So why is 0 even? Because there exists an integer, namely 0, such that 0 equals 2 times that integer. Alright, so n is odd if and only if there exists a k in z such that n equals 2 times k plus 1. So 19 is odd because there exists an integer, namely 9, such that 19 equals 2 times 9 plus 1. So these are formal definitions of what it means to be even and odd. Any problems with those? So let's really quickly prove if n is odd, then n plus 1 is even. Well, how do we do this?
Start out by using the definition of an integer being odd.
I'm going to start one step before that. Let n be odd. Okay, and we're going to show that n plus 1 is even. So this is our assumption or our premise. So yeah, use the definition of odd. We said that n is odd means that there exists a k in the integers such that n equals 2k plus 1. I'm out of ink. That's the definition of odd. When we know that n equals 2k plus 1, we're trying to show something about n plus 1. So over here on my ignore, we want to show n plus 1 equals 2 times some int. That'll show that n plus 1 is even. Well, I've already written n as 2 times some integer plus 1. And it may not be clear that this is going to be useful, but I'm just going to write down using that what n plus 1 is equal to. And that's just algebra. and I can combine that into 2k plus 1. That's more algebra. What can I do here? This is where the magic happens. Remember what I'm after.
2 parentheses, k plus 1.
There we go. Let's factor out a 2. More algebra. Now I've written n plus 1 in the form of 2 times an integer. I made a note to myself, that's what I'm after. Why am I after that? How do I get from there to my QED? To show that this is even, I have to show that it's 2 times something which is an integer. Well, I'm going to make the observation k plus 1 is an integer, and I'm just going to say properties of integers, right? K was an integer, so if I add 1, that's also going to be an integer. We don't have to prove that. We know that integers work that way. Well, n plus 1 is 2 times an integer. That means n plus 1 is even. And that's the definition of even applied to 6 and 5. And that's what we were asked to show. We're going to do 10 different forms of this proof over the next week or two. We're going to show that an even plus 2 is even, an odd plus 1 is even. We're going to show that the square of an odd is odd. We're going to show that if the square of a number is odd, the original number was odd. And similarly for even. And we're going to be able to rule the galaxy with all of that. So we're heading to good stuff. All right, take a look at the homework. Let me know if you have questions. And we'll continue with this on Wednesday.